With enough time, but I was feeling so lazy this morning.
On a day like this, you were feeling lazy?
Yeah.
Yeah.
I wake up like an hour and a half early on days like this. It just, my alarm go off?
I did not
I
want to
woke
get
up at
out
like
of bed.
7. But
I love this weather. I want to work in this weather.
I stayed in bed for an hour before I got up. I went to bed.
You know, you can kind of like turn it on your phone and just like browse that for a little bit.
Right. Play through like a little bit of every single program you've got.
I know, man.
Then check Facebook.
It hurts.
Then you gotta figure something else out.
You don't want to get up.
He's not gonna get nervous.
Try to decide whether you're gonna come to physics today or not. Never missed a physics lecture here.
Apparently, and a lot of people fight against it.
Oh, give everybody time. Give everybody.
I figure, I have no idea what any of this stuff is. I really don't.
So, just a word of warning.
Oh, yeah.
Evidently on Tuesday, there was somebody milling around in this room after I blocked the door open before class and kind of looking through drawers, and one of our lab support people came in, asked him what he was doing, said, "Oh, no, nothing, I'm fine," and then left. So we'll probably keep the doors locked now, so unfortunately. But if you want to get in early, let me know, and I'll open the door for you. We gotta kind of limit people milling around.
What the heck do you want here?
The only thing that's of any value, frankly, aside from maybe computer related per se, is the gram scale. And you can figure out why somebody might have a gram scale. We've had them stolen from chemistry before, and hence they started locking them up for that reason, which is pretty sad. If you can make money cooking drugs or selling drugs, you ought to be able to afford a $15 gram scale price. I don't get it, but then again, I don't cook meth, so I'm missing something in the process. Don't know. Okay, so we have electric circuits today to go through and to relate to what we've been doing. And it's all interrelated, whether we want to or choose to accept that aspect or that fact or not. Try to get as much stuff back as I possibly can.
Testing this.
Look at that.
I'm testing this out. It's not really doing it.
Probably just make it stand or something. Don't you have? Can't you attach it to this one?
Some of you have done some
Because
circuit
your head's going to be
analysis.
moving all the time.
Yeah, no, that's one thing. It's just testing. This
some
one's
point.
doing
You have.
everything, but
You've done some
I
amount
just
of
want to see what the
electrical
resolution
circuits.
is.
Small amount.
And it's
Small
like,
amounts, yeah, it's, and the key is I want to make sure a few basic points are emphasized. Whether you can do the nice Kirchhoff analysis of loops or nodes, that's fine, but oftentimes a lot of the obvious things get lost in the shuffle, unless you can sort of trip on it mathematically.
Just giving a test run here.
Oh, okay, I was gonna see what's going on there. I kind of like it, it's a nice look.
Yeah, I just want to see
You
if
know, the
it.
colonel's gonna go at you if he sees that beat.
Oh, you know what?
Flex him.
Yeah, he's never seen this yet.
Okay, so the idea behind electric circuits then is just looking at complete pathways for charge to flow through conductive mechanism, if you will. And to this end, let's just start looking at some examples. So let's assume that we have some sort of a simple electric circuit, and as I sort of alluded to last time, we can refer to this type of arrangement. Anytime you have things in a circuitous path, one to the next, we refer to that as a series connection. So, and this would be the equivalent of having two conductors or having one long conductor of some material with a calculatable resistance, and then snapping it in two, but running a wire between the two ends, if you will. So it's a nice analogy to think about from just our discussion of resistance and resistivity on Tuesday. So and to this end, then, these are attached to some power supply. I'm going to call it V0. We can give some value for V0. But I want to focus on a few basic things here. Now, to begin with, and this is a foundation for all of these processes, I've sort of drawn like little step diagrams for what happens when you go up and then back down in voltage. But I want to sort of emphasize that anytime you look at a complete connection of an electric circuit, and we refer to this type of a connection where you have a complete closed pathway for charge to flow, we call that a loop. So this arrangement is a loop circuit, if you will. We can add more loops by adding more closed paths around it. But fundamentally, it's a loop. Now, the thing about any loop is, and we make some basic assumptions. First of all, wires are conductors, as are resistors. But by inference, the conductivity, or if you will, the resistivity, is extremely low in wires or in metal connections than the corresponding resistances or resistive loads that it attaches. So everything we talked about with conductivity is absolutely valid from wires and metals, as well as our typical carbon resistor element. The difference, though, is that when you put them and connect them together, you have essentially negligible resistance compared to these larger resistances that drive how the charge will flow in the first place. So the rate limiting aspects of the process, or of the charge flow, are these resistive loads, not the wires. So typically we say that even though technically voltage will decrease and will vary as you go along any conductor, whether it's a metal wire or otherwise, we assume that for all practical purposes, whenever you look along a complete wire connection, we assume that the voltage does not change. It's a constant electric potential there. So whatever the potential is here, if we have a power supply of some voltage, typically the long end, when it's described this way, is the positive end, and the short connection is the negative end. Typically, whatever the potential is, the electric potential is just on the other side, or in the positive connection of the power supply, will be the same all along the wire to the point that it attaches to some other element in the electric circuit. Now, the one condition where that is not the case, and where the voltage across a metal wire matters, would be if I took this wire connection up here and attached it to the negative end of the power supply. Because now all of the potential difference, all of the voltage drop, all of the work required to push charge through the electric connection would only go through the wire, and there's nothing else but the wire that limits the flow of the charge. Now, typically we would call that a short. You short a circuit or short a power supply. You just run a wire to the ends. But as long as anything else is attached, the wire will never be the rate limiting factor in how the circuit runs or how the charge flows. So basic assumption is wires are just there to allow flow between the other resistive elements, and all of the work done is happening, or all the energy transformations are happening across these resistive elements that are ultimately the most influential aspects of the conduction. So if we start at one end and we make these assumptions, if the electric potential is a certain value here, the positive end of the connection of the power supply, all along this wire it will be the same. So you'll have the same positive electric potential here at this end. Whatever it is here, that's what it is over here. Now, let's put a value in for V0. So let's say V0 has a value 9 volts, whatever. V, but it does not mean V. It means the difference in electric potential between the two. And one of the things that's always hard to fully appreciate, I think, until you start adding a bunch of other things to it, is that it's never an absolute. It's only a potential difference, because it's only the potential difference that drives the work or the energy flow as the charge crosses or passes through a circuit. We don't care what the absolute values are, only what the differences are. So we call it V, but it's really a delta V for the power supply. It's what drives the charge in the circuit, and that's very important to mention. It's an escalator that takes you from one floor to the other. But just because you're on the bottom floor, it does not mean you are at zero elevation. And there's an inference to that in one of the chapter 24 worksheets on electric potential. Ivan and I talked about that yesterday in my hypothesis. So just make a note of that. Whatever the potential is here, all I know is that it's 9 volts above what it is on the other side of the power supply. If I wanted to, I could connect this end of a power supply to some sort of a ground or to some other reference. I could plug this into the positive end of another power supply so that hypothetically this could be 12 volts or some other value. Then what's important though is that this value is 9 volts above whatever that value is. And that will be driven by whatever happens inside this power supply. Okay, so there's no absolute here. And for those of you that had some electric circuit, we talk about grounding the circuit. That just gives you a reference. It's not zero. Zero is infinity. Okay, in an absolute calculation sense, zero means a million miles away. When you ground something and call that zero, all you're doing is giving a reference, just like you give a potential energy reference when you say the floor has zero elevation in the origin. And then we say, well, how high is something lifted up to calculate potential energy? That makes sense? Again, it's subtle, you never worry about it in an electric circuit analysis class, but it's important to sort of at least appreciate it. So we've got this relatively uniform electric potential all along the wire, and then something happens here. Well, if charge is flowing through this, and we'll say that charge is an electric current, because it's a connection, say that this is some current. I think the textbook uses big I. I'm just so used to using little I, I'm not going to change my notation now. It's going to take work to drive it across this. When it gets to the other side, it's going to have a lower potential than it did on this side. How do I know that? Because whatever charge, whatever energy the electric charge has before it reaches here, it will be lower by the time it gets to the other side.